Okay, folks, so yesterday then we reviewed our basic trig identities from Algebra 2. And again, first and foremost, what's an identity? What is an identity? What's that? So first and foremost, it's an what? It has an equal sign. It's an equation. It's an equation that is always true no matter what you plug in for the variable. X plus x equals 2x. No matter what you plug in for x, if you add it to itself, it will always be the same as 2 times of it. X plus x equals 2x. No matter what I put in, it will always be true. That's an identity. So we had from trig last year then our basic identities, that being the reciprocal identities. Is everybody comfortable with the reciprocal identities? The quotient identities, tangent is equal to sine over cosine, cotangent is equal to cosine over sine. So we've got our basic identities, the Pythagorean identities, and again, these are the 3 that I would encourage you to memorize. I know all 3 of these ones. I don't know all 9, but I know the 3 basics. Okay. If you don't want to know all 3 of these, you've got to memorize what? The first one. Cosine squared plus sine squared equals 1. Now, how did we get this one in this one then? But by dividing everything either by sine squared or cosine squared. Okay? So our Pythagorean identities. Was everybody okay with the example that we did yesterday? If we know one trig function, can we use identities to find other ones? Okay? And now again, we're used to drawing reference triangles. And if I know tangent, that means I know the opposite and the adjacent. Well, then I use Pythagorean theorem to find the hypotenuse. And then I use my baby trig. We're comfortable with that. But we also need to be able to use the identities as well. So is everybody all right with how we came across this one yesterday? Okay, well, we used the Pythagorean identity with tangent squared. And that was allowing us to find secant squared. Well, if I know secant, then that means I automatically know cosine, and then if I know cosine and tangent, I can use sine by using the quotient identity. So everybody all right with that one? All right, very good. Okay, so the next set of identities then are the cofunction identities. We talked about the cofunction identities, again, last year as well, so let's bring this light back up here again, okay? What kind of a triangle do we have here? We've got a right triangle, correct? Okay, so angle C is our right angle. Then what is the relationship between angle A and angle B then? They have to be complementary angles, right? Because what do the 3 have to add to? Well, if one of them is 90, then that leaves me what for the other 2? 90. 2 angles that add to 90 we know are complementary angles. So angle A and angle B are complementary angles. And now let's look at this down here. Sine A is equal to what? Y over R. Is everybody all right with that? Here's angle A, opposite over hypotenuse. Find another Y over R up there. Cosine of B, right? So what's the relationship between sine and cosine? They are cofunctions of each other. And A and B are, that's what we just started with. A and B are complements of each other. Cofunctions of complementary angles are equal to each other. Cofunctions of complementary angles are equal to each other. That's what the cofunction identity deals with. Cofunctions. What are cofunctions of each other? Sine and cosine, tangent and cotangent, secant and cosecant. Now, that's not a familiar pairing that we're used to, though. We're used to pairing sine with cosecant, tangent with cotangent, and secant and, secant and cosine. But that's what relationship? Not inverses. That's reciprocals. There's 2 sets of pairings for those 6 trig functions for us. There's the cofunctions and the reciprocals. Okay, so we got the reciprocal basic identities and then the cofunction identities. And the cofunctions deal with complementary angles. Cofunctions of complementary angles are equal. So here's my cofunction identities then. The cosine of theta is going to be equal to the sine of the complement of theta. Well, what's the complement of theta? If my theta is 30, what's the complement of 30? And how'd you get 60? 90 minus 60 is 30. Well, we're not using degrees, we're using radians. So the cosine of theta has got to be the sine of pi over 2 minus theta. Okay. The tangent of pi over 2 minus theta has got to be equal to the cotangent of theta, because these things are complements of each other. If we added pi over 2 minus theta, we added that to theta, we would get what? 90. We'd get pi over 2. We'd get the 90. And sine and cosine are co-functions of each other. So co-functions of complementary angles are equal. Okay? So if I'm dealing with some trig expression and I recognize a pi over 2 minus some angle, co-functions. Co-functions. I can get rid of that pi over 2 minus whatever the angle is and say it's the co-function of the complement of that angle. Okay? So co-function identities. Okay, so now we got 4 sets, right? The reciprocals, the quotients, the Pythagoreans, and the co-functions. Okay, all repeated from last year. Hopefully now just a little more light on them this year and a little better understanding of them this year. Even odd identities then. Even odd identities deal with negations of angles. The sine curve. Tell me, is the sine curve even or odd? Is it symmetric about the origin or is it symmetric about the y-axis? Sine. It's odd. It's symmetric about the origin, right? Okay. Symmetric about the origin. So what that means is that if I have the sine of a negative angle, what have we always done with negative angles? If I had a negative 20-degree angle, what did we do with negative 20 degrees? Because we don't want negative angles. We found a coterminal, right? We added a 360 to say it was whatever. Well, this gives us a way around it as well. If I'm dealing with an odd function, and folks, 4 of our trig functions are odd. What are the only 2 that are even? Cosine and secant. Cosine and secant, those are the only 2 that are even. All the rest are odd. Well, if I have an odd trig function, the sine, tangent, cosecant, or cotangent of a negative angle is the same as taking the negation of that function in the positive angle. So basically all I need to do is move that negative from the angle to the front of the function. What if I do if I've got an even function of a negative angle? I just ignore the negative. Cosine and secant of a negative angle, we just simply do what? We just simply drop the negative. We just simply drop the negative. Okay? If you look at like a first quadrant angle, first and fourth, they're right next to each other. Okay? Well, the cosine of a 30 is the same as the cosine of a negative 30 because it's symmetric about the y-axis. They're going to be the same on both ends. So I can just drop the negative. So the cosine and secant of a negative angle, we just drop the negative. It's the cosine and secant of that positive angle. But the odd functions, I move the negative from the angle out to the trig function. Okay? That's easier than adding 360 or adding 2 pi. If I've got a negative angle and it's an odd function, move the negative from the angle to the function. If it's even, just get rid of the negative. Just simply get rid of the negative. Okay? So we're used to saying something like, well, what if we had to find the exact value of the cosine of negative 135 degrees? Well, what we would have done is we would have added 360 degrees to that. We don't want to deal with angles that are outside of 0 and 360. We want everything to be inside of our circle. Negative 135 is not. So we found a coterminal. We would have added 360 degrees to that. We no longer have to do that. I just need to look at cosine and say, okay, cosine, is that one of my evens or is that one of my odds? Is it symmetric about the origin or is it symmetric about the y-axis? Symmetric about the y-axis. It's an even function. So the cosine of a negative angle is just the same as the cosine of its absolute value. And now I can say, okay, well, that's in quadrant 2, where cosine is what? negative cosine, my reference there is a 45, negative radical 2 over 2. So if we're dealing with negative angles, we've got to determine if it's an even or an odd function. And if it's even, you just drop the negative. If it's odd, you move the negative out to the front. You move the negative out to the front. Okay. 5 sets now. Cofunction identities. Sorry, even odd identities, not cofunctions. We just did the cofunctions. All right. Why all of these identities then? Well, we can use these identities to simplify expressions. And if we can use them to simplify expressions, then maybe we can use them to help prove identities. Remember last year when we had to prove identities? Okay. These were our trig proofs. Okay, so you remember your proofs from geometry? How you kind of set up the 2 columns? Well, our proofs in trig are similar. We just don't have a statements and a reasons. We just draw a line down through the what? What's an identity again? It's an equation. We drew it down through the equal sign, right? Why did we draw that line down through the equal sign? What were we not allowed to do? We couldn't switch terms from side to side, right? I couldn't add 2 to both sides or subtract off a cosine theta from both sides. I was only allowed to work on one side at a time, right? Could we work on both sides? Yes, we just couldn't switch terms from side to side. I could work on one side and do what, and work on another side and do what? Simplify. And by simplifying, we tried to turn everything into what or what? Sine or cosine. We tried to recognize if there were what kind of identity, because they're easy to spot. What are the easiest identities to spot? There's 9 of them. And how do you spot them? 1 plus or minus something squared, or something squared plus or minus something squared. Okay? So we use these identities, the basics, the reciprocals, the quotient, the even odd, the cofunctions, and the Pythagoreans to be able to simplify sides. Okay, so do we have an identity up here? There's an equal sign up there somewhere? No, we don't have an identity. We just have an expression. Well, this expression might be on one side of the equal sign. And what we'd have to do with this is try to simplify it down. And if I can simplify this down, it's easier to prove the identity. Okay? So, how many terms do I have here, folks? No. There's 3 values up there, but there's only how many terms? 2 terms. How do you know there's only 2 terms? Because there's only one operation up there, right? It's this thing added to this thing. There are 2 terms up there. Do those 2 terms share something in common? Absolutely they share something in common. They both have a what? They both have a cosine x, right? How many cosine x do we have right here? 3 of them. And over here we have, so let's factor it out. If I factor out my cosine x, what does that leave me with here? Cosine squared x. Plus, what does that leave me with over here? Sine squared x. And now, what do we have the possibility of? We now have the possibility of a Pythagorean identity because we have a square plus another square, right? And that happens to be the Pythagorean identity. Bless you. What is cosine squared plus sine squared equal to? 1. So cosine x, and folks, that is an important step to show right there. You're showing your Pythagorean identity that you know that that's equal to 1. And then anything times 1 is cosine x. Can we go right from there to there? No. No, because you haven't shown that this is equal to 1. You haven't shown your use of the Pythagorean identity there.
Would you have to show the angle at all?
No. No, you leave your variable in at the angle. Now, if there was an angle in there, if they had like a, when we get to the sum and difference ones, we're going to have one like cosine of pi over 6 plus x. And we're going to expand that summation out, and then we will definitely plug in the numeric substitution for the cosine of pi over 6 and the sine of pi over 6. But here, no, we don't know what the angle is. We leave it x. Okay? So what I've done now is I've simplified this side down. Now instead of having two terms, we've simplified it down to one term. And it is one of the two basic trig identities, cosine x. But what we have now is if we had some other expression on the other side, we could try to simplify that side down to be cosine x as well, and then we would have proven the identity. But folks, we can't prove identities until we are comfortable simplifying. Recognizing identities and simplifying down. Okay, and factoring is always involved, usually with simplifying down. Are we all right with that example? Okay, let's see another one. How about this one? What is indicated for me to do on this one? FOIL. Does everybody see the FOIL here? What do parentheses mean? Multiplication. Well, inside of those parentheses, I got binomial. So I got a binomial times a binomial. I have to FOIL. I've got to FOIL this out. Okay, so what's cosecant x times cosecant x? Cosecant squared x. Now I'm potentially going to have a what? As soon as I've got a squared term, I'm potentially going to have a Pythagorean identity. So I'm going to FOIL this out. We're going to get a cosecant squared x. Now this FOIL happens to be multiplying two what's together? Very specifically, binomials that differ only by their connecting sign. Conjugates, we're multiplying two conjugates together, right? Do we have to do the full FOIL when we have conjugates? What are we able to skip? The inner and outer part of the FOIL. We only have to do the first and the last. Okay, so what's the last? What's negative 1 times 1? Minus 1. So the top simplifies down to that. The bottom, I still have my cosine squared x. So I've done the FOIL. I now have a potential what? Pythagorean identity. How is there a potential Pythagorean identity here? What made you recognize that? The square minus 1. The square minus 1. Okay? Now, hopefully you get, C's go together. I'm glad you said that because that's how I remembered them yesterday. The C's go together. What two C's, though? Because there's three C's. What two C's go together? Cosecant and cotangent. Because cosine has to go with sine. Cosine and sine go together. Okay? So what we had yesterday is 1 plus, and it's always 1 plus the tangent, or cotangent. So 1 plus cot squared was equal to cosecant squared. 1 plus cot squared was equal to cosecant squared. So those are the two C's that have to go together. All right, well, can we rework that around potentially to get cosecant squared minus 1? Yeah, if we subtracted 1 over here, we'd be left with what? And then over here we'd have? So cosecant squared minus 1 is equal to? Cotangent squared. So cotangent squared x divided by cosine squared x. Still more that we can do here, though. Again, our goal is to try to get everything in terms of what or what? Sine or cosine. Well, we've got a cosine in the bottom, but we don't have up top. Quotient identity, right? Cotangent squared is equal to? Cosine squared x over sine squared x. Cosine squared x divided by sine squared x. And folks, instead of dividing, we can do what? Multiply by. So let's multiply by the reciprocal of cosine squared. Well, cosine squared is cosine squared over 1. What's the reciprocal of that? 1 over cosine squared. So let's multiply by 1 over cosine squared. Multiplication. Is multiplication the easier process with fractions, or is addition the easier process? Multiplication is much easier. We don't have to have a what? We don't have to have a common denominator. And all we do is multiply straight across, right? Top times top, bottom times bottom. But what can we do before we multiply if we recognize it? We can reduce like terms, right? Is there anything that will cancel out here? Cosine squared in the top, cosine squared in the bottom, they knock each other out. I'm left with what? I'm left with what? 1 over sine squared x. Or cosecant squared x. Would either of those be acceptable? Absolutely. 1 over sine squared x or cosecant squared x. Okay. So what I've again done here, folks, we're eventually going to get to the proof where we might have to work on both sides. Well, what do we do on the individual sides? We do what we've just done. We've got to try and simplify that one side down. And then if it doesn't look exactly like that other side yet, well, we're going to go to that other side and we're going to simplify that other side until we get common ground. And then once we have the common ground, we're good to go. Okay? But we've got to get very comfortable with this stuff. We've got to get very comfortable with understanding, okay, I recognize a multiplication here. I've got to FOIL these out. Or I recognize that these two things have the same. I can factor it out. What would we do with something that would look like this? Cosine squared x. Let's go plus cosine x minus 12. What can I do here? I can't take out a cosine. 12 doesn't have it. You're thinking the right concept, though. You were going to do what? You were going to factor. You were going to factor a GCF. Well, if there's not a GCF, we then go to dots. There's obviously not dots here, but this is a what? This is the general trinomial. Can I factor this? Yep. What multiplies together to give me cosine squared x? Cosine x and cosine x, right? So I set up my two parentheses. Cosine x, cosine x. Tell me about my signs, please. They're one of each, right? One's got to be plus, one's got to be minus. All right. What are the factors of 12? 1 and 12, 2 and 6, 3 and 4. Which pair is going to subtract to a positive 1? Positive 4, negative 3. We've got to be able to recognize things like that. Okay, we've got to be able to recognize factors that we can run out through. GCFs, dots, trinomials, maybe even factor by grouping. We can all do that with trig. Okay, we can all do that with trig. Okay? And recognition of it is very important. The recognition of those are very important. Okay? How about this one? Let's use identities to help solve this equation. And they want me to solve for x in between where and where? 0 and 2 pi, right? Now, can I include the 0? I can't include the 0. Can I include the 2 pi? Why not? How do you know? Parentheses. I need a bracket to include it. Well, why are they not having me include 2 pi, but they are having me include 0? Is 2 pi the same as 0? Yes. 2 pi is the same as 0. It's your full circle. You're all the way back around to 0 again. So that's why you're including one but not the other. All right.
Cody Hyman, please report to the office.
First goal is usually to try to do what? Sines and cosines, right? Is there something I could do here then? Tangent, right? Okay, so I'm going to look at sine cubed over cosine x is equal to sine x over tangent x, right? I'm sorry, sine x over cosine x. Thank you. Folks, if two fractions are equivalent, the only way two fractions can be equivalent if what? How many parts are involved in a fraction? 2 parts. The fraction has a what and a what? A numerator and a denominator, right? Well, the only way two fractions can be equal is if and only if what is equal? The denominators are equal and the numerators are equal, right? That's the only way two fractions can be equivalent to each other, is if their bottoms are the same and if their tops are the same. Well, what do we already have here? We already have their bottoms are the same, right? Do we even need to worry about fractions anymore then? No. What's the equation we're trying to solve then now? Sine cubed x equals sine x, right? These two fractions are equivalent. Their bottoms are already equivalent. Their tops have got to be equivalent as well. Sine cubed x has the equal sign x. Well, this is just like saying a cubed is equal to a, or x cubed is equal to x. We've got a polynomial equation here, right? What do we always set our polynomials equal to? 0, right? We always set them equal to 0 right here. So what would we get? Sine cubed x minus sine x equals what? 0. Now we can take out a what? We can factor out a sine x.
May I have your attention, please? The afternoon announcements.
What would that leave me
There
with?
will be no late buses today. Just a reminder, the golf match today has been canceled.
Still equal to what?
The varsity baseball and softball games for today have been canceled. Participants in the Franklin's Got Talent, please.
0. Factor property now tells me what? We set them both equal to 0, right? We set them all equal to 0.
See Ms. Krieger before you leave today. The girls' varsity softball game for tomorrow has been canceled. The boys' varsity baseball game for tomorrow at Cat Little Valley is still on. Bus time is 1:30 and will be picked up at Skateland. Juniors who sign up to walk in the parade tomorrow should meet at the junior booth at 10:30. Attention National Honor Society members. Check My Big Campus for 2 service opportunities during the Maple Festival. Please consider volunteering your time for these events. They mean a lot to both our school and the community. There's still time to register for the 2015 Maple Festival Staffs Race. Registrations will be accepted until 5 o'clock tonight. Please visit the registration website via the orange flyer to register or see any student council member. On Sunday, at the end of the Maple Festival, Franklin's Got Talent will present 10 awesome music and dance acts. The competition begins at 5 o'clock in the high school auditorium. Tickets are available at the door for $3. Come and support your friends as they entertain and amuse. Following students, please report to the office. Michael Frank, James Galetta, Tim Knight, Jacinda Twilliger, Nolan Palmatier, Aiden Barrington. Have a great weekend, everybody. Come out and enjoy the Maple Fest.
We never solve an equation without doing what? Checking it at the end now. Can we store all 4 of those values as x and plug it into the very original? Yes, but how do we type sine cubed x into the calculator? We have to use parentheses, right? We're going to go parentheses. Sine gives me another parentheses, which we're going to put inside of it what? The x, and then close to cube it. We're going to run through those. Okay? Is that the last we've got on 5-1, folks? Okay. Okay, so we're going to be looking at 5-1 on Monday then for our homework assignment then. Very important through here, folks. Very important in 5.1.